Good. So before the break, we went into some depth about the Poisson distribution and how wonderful it is and how much it captures of football because of the inherent randomness in football. What we're going to spend the rest of the lecture on today is basically using that then to construct a statistical model which will allow us to test various hypotheses. I'm going to come to how we do it over time, but one thing that we can do quite simply is before we start like fitting the model, let's just assume that you think that Manchester City score 2 goals on average and Everton score 1 goal on average. This is from something which I've done. The link is at the bottom. I did this for a few years ago. And City were going to play Everton. And just to illustrate, again, the power of the Poisson distribution, if I assume that City scored 2 goals, so the Poisson parameter for City is 2, and the Poisson parameter for Everton is 1, then I can actually simulate all different results. It's not even simulation, it's just picking out from the equation we gave here. So we put 2 in for City and 1 in for Everton. Putting those in, we can actually pick out how many goals the two teams will score, and we can quite easily just make a graph like this. So this isn't based on even simulating anything in the sense that we run a computer simulation. It's just based on sticking the parameter 2 into the Poisson distribution for City and sticking the parameter 1 into the Poisson distribution for Everton, and then making a list of the different results. So 5-0 is quite unlikely because the average goals is 2, while something like 2-0 is much more likely. And see, in fact, 2-0 is the most likely score in this case, even though 2-1 was the average goals that we would expect from the two teams. So this gives situations where City wins, situations where Everton win, where it's a draw, and situations where Everton wins, all directly from the Poisson distribution. But what I've done there is I've actually assumed in advance I know that City score 2 goals on average, or I expect that from the match in order to calculate probability. What we'd like to do, what we prefer to do, is estimate that from data from previous matches. Again, this one is based on estimates of data from previous matches. This is something I did in Soccermatics. I took the scoring rates of clubs during 2012-13. Then I simulated what might happen in the 13-14 season on the basis of that. And you can see here, Manchester City did win that season. And you can see some of the simulations they win. Here we have Liverpool second, Chelsea third. This is just a random selection of the simulations, or a selection of the simulations in order to illustrate that point. We get these types of results out of it. So we could also get, based on the scoring rates from the previous season, that Liverpool might have won that season. And these things give reasonably convincing models of what happens over an entire season. But this is what I wanted to emphasize. I'm going to come back to how we actually do these simulations in a bit, but what I want to emphasize beforehand, these models aren't perfect. They tend to they underestimate the best teams. If you notice here, City won by far more points than 73. In these recent seasons, we've seen City and Liverpool on like 99 and 100 points and things like that. That's not going to be predicted by a Poisson model because it's always just a little bit too conservative. So they're never perfect for the number of points. And that's partly the nature of the model. This is small things that don't quite work with the model. Plus, it's partly that it's difficult to estimate the scoring rates for the teams. So one thing we can do, for example, is we can use expected goals early in the season to simulate future matches. So these simulations, they kind of work. They're not very far away, but they're certainly not perfect either. And that's evidenced by the fact that the best teams slightly overperform what the model would predict. And also the worst teams tend to underperform what the model would predict. They sort of make things a little bit more even than we'd like them to be. Okay, to summarize, football's chaos makes it predictable. Goal distribution can be found. This is what I think is one of the coolest things. It just with one parameter, you can find the whole distribution of things, and you can even predict very reasonably the results of a match. You can predict the results of a season using those types of things. Scoreline can be predicted. Draws tend to be a bit wrong for different leagues. That's what bookmakers spend a lot of time adjusting for. You can simulate the league easily. And what we're going to look at now is how you can find these as indicators of good football. This simple model of Poisson goals is really difficult to beat. It's very, very difficult to beat. And you don't see people beating this model very often. The bookmakers' odds slightly beat this model, but really this simple model is difficult to beat. Okay, so how do we estimate the parameters? And that's the problem that was solved by Dixon and Coles, which was mentioned in the chat. Beautiful paper, 25 years old now, incredible, where they said, okay, goals are Poisson distributed, seems to be the case. What we need to do is have a model to estimate the parameters for this Poisson distribution. So here they've written down the joint probability of the home team getting X goals, the away team getting Y goals. And the main part of it here is the Poisson distribution here, that you have lambda X, which is the lambda is the rate at which the home team scores, mu is the rate at which the away team scores, and you have two separate parameter values for both of those teams. And equivalently, you can say, as we do down here, get my laser pointer out again, as we can say down here, we can say that, well, the random variable which describes the scoring rate of the home team against the away team is Poisson distributed with three parameters. One is an estimate of the quality of the home team's attack. The beta j is an estimate of the away team defense, and this gamma parameter is the home advantage parameter. And all of these things can be estimated using Poisson regression on the data. And that's what we do in the code. We try and estimate these separate parameters. See, in this case, they're multiplicative. I think normally you would use multiplicative parameters. So this thing is going to be like 1.1, for example, if a home team is particularly good in attack. Beta J, a good away team defense, is going to be 0.9, so it reduces the probability. And then the home advantage is going to be some particular value. So I think it's 1.2 or something like that, multiplying the number of goals that you're likely to score. There's this lovely data set collected by at footballdata.co.uk, collected by Joseph Bookdahl, I think his second name is. Brilliantly collated data set which allows you to fit models, or which tells you just the results of the matches, which is all we really need for this type of model. So if I load up that data, I get to be honest, when I first did this fitting of the model, I did it at the point when the season had been postponed, or we didn't know what was going to happen about Corona and so on, but it gives a nice data frame full of both the odds for the games and the number of goals that were scored and so on. And so you've got all of that. And so when I did it, we actually didn't know what the rest of the season would look like. And so it was a good point to try and simulate out the rest of the season. Now, actually, we have all of the data from last season loaded into this. And we are going to use stats models again, one of my favorites packages for doing statistical modeling. It does the more sort of traditional statistical models, the kind of things that Dixon and Cole would be doing. Load in goal model data, makes if I do this, goal model data, is it head? Actually just gives us the goals that Liverpool scored against Norwich, for example, West Ham against Man City. Simple data set of this type. Then this is code. I want to emphasize that this is code I got originally from a very nice blog about predicting models using Dixon and Cole. You can go in and have a look at that. But they basically use the Poisson model in statistical models to fit the goals as a function of the home team, home advantage. This is a home 1-0 if the team's at home, the team, the opponent, and so on. And then we're going to later, so we can fit this model. There we go. And once we have that that model, we can actually have the coefficients for every one of the teams. So in this case, a coefficient, I'm going to go into this back in the lecture, but a positive coefficient indicates a good team, a negative coefficient indicates a bad team. Arsenal, because it's alphabetically first in the list of teams, that's actually been picked out as the benchmark team. So what these tell you are, is a team better or worse than Arsenal? So Aston Villa are statistically worse than Arsenal, Bournemouth are statistically worse than Arsenal, Chelsea are statistically better than Arsenal, Manchester City are a lot better than Arsenal. So no surprises there. We'd be surprised if it didn't come out with these types of things. That's in terms of scoring goals, and then in terms of conceding goals, Aston Villa concedes statistically more goals than Arsenal do, and so on. And then what we can do is, once we've got those rates, we can start to actually simulate matches, and that's what the rest of the code does. I've found that the scoring rates of Manchester City is 2.6. Arsenal against Manchester City are expected to score 1.16. And this one, I think it's nice just to run this a few times. So this is just some matches. Well, that was Manchester City Arsenal. That was meant to be the match that would be the first match after the break. And there you go. I just ran the simulation. Came out 2-2. So that should be the result. Now, I'll do that again. Run it again. No, Manchester City lost. Oh, now they won 4-0. Just keep doing 5-1, 3-1, 3-1. I'm surprised that I've got these results. Well, there you go. We've got the randomness in football. You really get an idea for these things. 4-2, 8-1. Okay, that's incredible. So you can run these things and you get different results, but that's not really the most, it's not the most scientific way of predicting the results. What you need to do is simulate it lots and lots of times. And that's what the last part of the code does. And it makes one of these very pretty figures, which tells you the probability of different outcomes. So the most likely outcome in all these simulations is 3-0 to Manchester City. Then you have 1-0. Some of these results we got for Arsenal were very unlikely based on this, but that's the feature of randomness. So this gives you a matrix. So the probabilities, it's like any of the heat maps that we've done earlier. This is the probabilities of the different score lines occurring. Most of the things are clustered around here. About a 3-1, 2-1 type of result is the most likely, and then the less likely ones are further out here. Okay, let me go back to the thing. So you should definitely go in and have a play around with that code later. And that's exactly what we generated. Again, I thoroughly recommend this blog where they go through the details of how they did this fit based on the Dixon and Cole's model. But what's important here is that teams that are significantly better or worse than Arsenal, and this is one of the things that I want to get to the bottom of here, because if the coefficient is greater than, if the coefficient is positive, then the team is better than Arsenal. If the coefficient here is negative in this regression, the team is worse than Arsenal. But we should also look at the probability values, because when we do these statistics, we actually want to find out, are teams statistically better or worse than Arsenal? Now imagine from Arsenal's perspective, how they're thinking about these types of things. So they want to be a top 4 team. So they can accept maybe that Chelsea, but they can accept maybe that Manchester City and Liverpool, who have been very strong recently, are stronger than them, but they are less likely to accept, for example, that Tottenham are stronger than them, or that Chelsea are stronger than them, because they're competing for those places in the top four. And this gives us some part of the answer there. Which teams are statistically over last season stronger than Arsenal? And you actually find that there's just, this one should have been red, but there's just two of them. Liverpool and Manchester City, they have p-values which are lower than 0.05, is what you would usually use as a cutoff. So only Liverpool and Manchester City, you could say, are statistically overperforming Arsenal last season. But on the other side, we only have three teams which are statistically underperforming Arsenal. And those are Crystal Palace, Norwich, and Watford. So all of the other teams are not indistinguishable, but they're very similar to Arsenal. And this makes it very problematic for somebody who's sitting at Arsenal deciding what they should do. They're basically statistically no different than how many teams? 14 other teams in the Premier League. They're not statistically different than Manchester United. Appear to be a bit better than them, but Manchester United aren't statistically better than Arsenal. Leicester did better than them, but Leicester aren't statistically better than Arsenal. So they can certainly use this to place themselves in a ranking of how well they performed last season, but they can't say, see, Spurs here, that's quite interesting. Spurs aren't any different than Arsenal at all. And so they can't really use this to give any strong evidence of where they are or where they're going. This makes it really difficult when you're planning a football club. The fans have some expectations about something you should do this season. You should qualify for the Champions League, and you can have those as a goals. But when you're actually reviewing the data, you find that you statistically aren't very different from most of the other clubs in the league. That was in attack. Same thing you can do in defense. Haven't illustrated the things, but again, if you look at the p-values, Aston Villa's defense weren't statistically significant worse than Arsenal's defense last season. It's actually very few. Norwich's defense was statistically significantly worse than Arsenal's defense last season. And even Manchester City's defense wasn't better. So these give really even results. And that's always a tension there, looking for these things which are really true statistical methods that you as a statistician or a data scientist would be convinced about, and what the expectations are about being able to say that certain teams are better than others. Nice thing there is home advantage is 0.2353 goals. So I thought that was a nice thing to bring in. There is still a home advantage. It seemed to disappear. There's quite a few studies looking at this, how it disappeared a little bit during the indoor corona times. So you could actually measure that using this type of model. And I think I've actually said this, so this is, I've emphasized this a lot in what I said about the coefficients. Statistically significant differences are remarkably difficult to find in football. And that's often why we tend to concentrate on looking at the style of play metrics, that we use a lot of heat maps and passing networks and things just to identify the style of play, because these things that we can actually measure more reliably, and even there we can't necessarily measure them in a statistically reliable way, but we can actually measure them more reliably and get more insight to them into them than just looking if we've won or lost football matches. It's really counterintuitive and difficult thing to understand, but we want to go deeper down into our understanding, because this overall, are we doing better or are we doing worse, just becomes a very difficult question to answer. Just now I'm working with Hammarby, and we're, I think, 7th in the league. And when we re-simulate the table based on expected and goals, realistically, we could be anywhere between 2nd and 8th. And this is a very difficult discussion to have, especially if you try and have it with players and coaches who are actively involved in lifting us up from 7th to 2nd or 1st. To tell them, well, we could have been anywhere between 2nd and 8th is really difficult for them to swallow. And it's very difficult for fans to swallow, but that's actually what the models tell you with the when you do look at these things properly. There's a wide range of places you can realistically expect to end up on any particular season. If the data told us that we were likely to be 15th or something, then that would be a real problem. But a span of 2nd to 8th when we're actually 7th isn't that bad. Well, it is bad, but it's not that bad. Okay, so I did one more exercise. If you go back into the back into the women's football data, last time when I presented this, I looked just at passes in my Poisson regression. So I just looked at this passes, and I found that passes were a statistically significant predictor of good football. And this time, in order to do it properly, I actually put in all of the teams into there. So I see that there is a team-related effect. And the p-values for none of the teams are actually statistically significant. I think I'm looking for the USA. No, even that. So actually passes turned out to be quite a good predictor. And that's one of the things when you do a regression of this type, if you're interested in a particular metric, such as number of passes, you should always correct. This is called, I've forgotten what it's called in statistics, where you have fixed effect models. So the fixed effects are the teams, and the passes is the variable you're interested in. What you try to do is you remove the fixed effects. If you're interested in a style of a particular thing, like passes, and the value that passing adds, you remove the team variable, because using these fixed effects variables, and you see that none of them are statistically significant. So passing the ball a lot at the Women's World Cup last time, as far as we can see from the data here, was a reliable sign of playing good football. I think that's quite a nice result. We removed the fact that, for example, certain teams pass the ball a lot, and we still get this result. So passing does correlate and does seem to indicate better football in terms of predicting goals. Remember, this was a Poisson regression of passes and all of these other teams onto goals. You can go back into file number 8 in the GitHub and do that analysis yourself. See that. I've got some very nice studies of this type. So what can you tell? A question came up about passing intensity. So this is another one. This is really, if you look in the academic literature compared to what you see written in, well, on Twitter or something like that, very seldom does it come up like what passing rates the teams have. So this is number of passes while in possession of balls. So number of passes divided by possession time. This is a study by Thomas Grund, who's a sociologist actually, and he was interested in the property of social football as a social network. And he tested passing rate. I'll come back to network centralization, but let's concentrate on, let's actually start with possession, because I said in an earlier thing that ball possession wasn't statistically significant. And so he looked at possession of the teams, he looked at intensity, which is passing rate, and he looked at centralization, which I'll come back to. And he created 3 models. The first model has no fixed effects. So you just do a Poisson regression of goals scored as ball possession. And he finds that that is statistically significant at the 1% level. But then he says, well, what if I put in a team effect? So he was studying the Premier League. And so if he puts in just like I did here for all of the teams playing in the Women's World Cup, he put all of the teams in the Premier League. And he said, well, if I do that, is possession still important? And then he finds out, no, there's no statistical effect of possession. And so that basically the possession part here is that at this time when he was analyzing the game, it was Arsenal and Manchester United who were the best teams. They had more possession than the other teams. And once you included them as the team, the statistical effect dropped away and possession was no longer a statistically good predictor of success. And then the last one, he puts in both the home team and the away team. That's like I did here, home team, here, away team. And then he found that, again, possession has no effect. In fact, possession, when you account for the teams, possession, if there is any trend, it makes the teams worse than better. Then network intensity, this passing rate I love a lot because it doesn't come up a lot in public discussions about teams. I know that some teams do use this. You basically divide the number of passes by the time in possession. And he found that this was statistically significant, definitely when you don't put in the fixed effects of the teams, and to a sort of small degree here, this was statistically significant at a 5% and a 10% level. This is something to be slightly skeptical about, but it does seem to be a reasonable pattern. So even accounting for the fact that teams are different, some teams are better than others, the regression indicates that passing tempo is more likely to produce good football and score more goals. So concentrating on getting your team's passing tempo up is a way to expect to score more goals. The last one he said is network centralization. I'll just tell you that he also found that two centralized networks, I'm going to say a bit about what centralization is afterwards, but before I do that, let's just say that two centralized networks, that means that the ball goes too often to the same player, tend to produce worse football. So the more distributed your game is, the better, the more likely you are to succeed. And he found this actually at a 5% level. It's a very nice paper, and this is how you want to do it. If you've got your metric you believe will predict good football in a particular way, you have to do this second, well, you have to do all three regressions, but you in particular have to do this last regression where you take into account team quality, which is sort of taking into account the quality of the players. I said centralized versus decentralized. I wrote a Medium article, which you can have a look at about this. One thing that could be noticed in this was in Ibrahimovic, it wasn't Pogba's first season, but Manchester United in this season, what was it, 3-4 seasons ago? Yeah, 4 if you count this season. Their passing networks, so this thickness of this, like you've seen in some of the other lectures, thickness of this is how often players pass to each other. Their passing networks were very, very focused on Pogba. Nearly all the balls went through Pogba, up to Rooney, and Ibrahimovic was also going through Pogba. And their results, though this one they happened to win, their results weren't quite as good as Liverpool, who have a much more decentralized style of play. And even if you look at Manchester City, they'll have more links between them, but they have a very decentralized style of football. And these are anecdotal pieces of information, but the Grun study shows that that's something to start looking for. If you can measure network centralization, which you can, I think some of the other talks have detailed how you do that. You measure the network centralization and you see, is your team playing too centralized? And if so, are they playing through a particular player? And there is a statistical reason to believe that you might have problems if you have that too centralized style of play.